Welcome to Anthropology lecture number 30. We'll be looking at mathematics, which you might be thinking, is mathematics anthropological? Well, mathematics is part of human culture. So definitely the creation uses, the way math works and functions in a society can be quite anthropological as part of that society's culture. So let's take a look at math as an example of human culture and the way the Egyptians did math, plus some Egyptian math problems. Ooh. In just sort of general theoretical terms, or even just definitional terms, math is a way that we measure. So this cow is so many units long. It's a measure of quantification. I have 5 cows. You have 3 sheep. And it's a way of essentially, if you get right down to it, of taking the world and reducing it to numerical representation. In its most complex forms, that's how you see math today. The math of physics, the math of astrophysics, incredibly complicated representations of the universe and what happens in natural phenomena. But at the everyday level, most of us just use math for measurement and counting. We need to know how much is in our bank account, how much is going to come out, how big is that bed going to be, and will it fit into our bedroom, or we'll have to get a different size, which picture frame goes best with this size picture. Those are the kinds of things that we're definitely concerned with on a day-to-day basis with mathematics. I would argue too in school, mathematics probably most important in terms of, do I have a 91 or 93 for this quarter? Those kinds of numbers. Obviously, that tells us that numbers are very powerful for us as representations of reality, that they are reducing complex human phenomena to a couple of digits on a piece of paper. Did the ancient Egyptians think of math that way? Let's find out. Egyptians primarily, like many of us, used math for accounting purposes. So we have land that we need to figure out how much land there is there, what portion of that is going to go to the king. We need to divide up produce and the production of materials, so some can go to support the workers who are building the king's monuments. So a lot of accounting purposes. And Egyptian mathematical texts, there are 2 major ones, are essentially lists of problems. Here's a problem, here's how you solve it, here's a method for solving it. Egyptians are obviously, in terms of you look at the pyramids, pretty good at geometry and representing not just units of measurement, but also space itself, and understanding how to calculate the volumes of different objects, the area of an object that it's going to take. Because obviously those things practically mean either your building's going to stay up or not. There's no formal sign for a zero, though we think the Egyptians kind of understood the quantity of zero, the idea of something being empty, not being there. We see evidence of that in some of their calculations, but no actual like symbol for that. We know that they could approximate pi. They did have a method for getting to that particular number. It's not exact, it's not perfect, but they certainly were aware of the idea of it and measuring that. And the Egyptians also worked with fractions. So they understood partial quantities of numbers. I don't have one thing, I have 1/2 of a thing. So conceptually, they were able to deal with fractions as well as whole numbers. Here are the signs for Egyptian numbers. Um, so you can see here that these signs represent powers of 10, right? 1, then we go to 10, then we go to 100, and then 1,000, 10,000, 100,000, and a million, which for lots of Egyptians, a million simply almost kind of meant, we don't know, it's uncountable, it's so many, millions and millions and millions and millions. How do you then make other numbers? How do you make something like, I don't know, 458 in a system like this? Well, you group all of these numbers on the left into groupings to represent all the other numbers. So for example, 152 is a 100. That gets you to the 100s place. It's 5 of these 10s here. So loop, 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 loop. And then 2 of the 1 marks. And so any number can be represented for the Egyptians simply by using these place markers additively. So 5,400 is 5 of these thousands, and then 4 of these symbols for 100. So how did the Egyptians actually do math problems with a symbol like that? You can imagine it's kind of difficult to do work when you're writing in symbols like that, but the Egyptians certainly did. And they engaged in good old addition and subtraction as well as multiplication and division. So we're going to practice a multiplication problem together. Think if I gave you two-digit multiplication, 47 times 24. You probably haven't done that for years because that's what we have calculators for. So why would you ever want to like just do that by hand? But I did. Our methodology is to multiply each part of the number by the number above. So we take 4 times 7 and then 4 times 4, and that gives us 188. We put a 0 here because this is over 1. So 0 is our placeholder. And then it's 2 times 7 and 2 times 4. 188 plus 940 gives us 1128. So that's our two-digit multiplication system that we use. The Egyptians don't do it that way. It's a little bit different. The Egyptians conceived of multiplication as essentially doubling. So you find an appropriate amount of doubles that will get you the two numbers that you start with. Which it's an interesting thing to think of, but it actually works. So if you want to multiply 47 by 24, you start with the 24 and with a 1. That's the base number you can start with. And then you double it. 1 to 2, 2 to 4, 4 times 4 is 8, or 4 doubled is 8, 8 doubled is 16, 16 doubled is 32. So every time you're multiplying by 2. You do the same thing for 47, the number that you want to multiply by. So 47 doubled is 94. 94 doubled is 188. 188 is 376. 376 is 752, and then 1504. You're probably thinking, what the hell? How does this even make any sense? Why would doubling numbers make sense? So here is where the genius steps in. 24 can be made up by adding some combination of these numbers here on the right. So how do you get to 24? Well, I mean, it's 24 ones. It's 12 twos 12 times. But probably simply easiest is to say it's 16 plus 8. And indeed, 16 plus 8 is 24, because 16 plus 4 is 20, plus another 4 is 24. Here's where the Egyptians said, aha, now that tells us the answer to our multiplication problem. If you look over here, 8 and 16 make up 24, 376 and 752 will tell you now what happens when you multiply 24 by 47. If you add 376 and 752, you get 1128. One scholar has essentially pointed out that Egyptian mathematics, in terms of multiplication, is very similar to the way computers compute today. It's a system of essentially ones and zeros. This 24 is represented by 0, 0, 0, 1, 1, 0 here. So these two are on and the others are off in order to make 24. I think you can make too much of this point of view, but you certainly might encounter that on YouTube, because there are several versions of this video out there. But it is an interesting way of thinking about the act of multiplying that we take for granted as just being, I'm going to multiply by 4 here and then 20 by here, which is essentially what you're doing in the form that you were probably taught as a kid. Because I'm going to do 4 47s and 20 47s, and that will give me 1128. You try now. Try 353 by 57. So we got a 3-digit number and a 2-digit number. I'll wait. Did you figure it out? I mean, the old-fashioned way works pretty good. It's essentially 7 times 353 and then 50 times 353, which gives us 2121. So 57 353s is 20,121. The Egyptians would thought of it this way. 1, 2, 4, 8, 16, 32, 64. I didn't have to go to 64 because 64 is already bigger than 57, so I can't add this to anything else and get 57. So instead, I could start with 32 and see what would I add to 32 to get to 57. Well, 32 and 16 and 8, and then to make it 57, we'd need a 1. So 32, 16, 8, and 1 is 57. Over here, we circle the corresponding values, 353, 28, 24, 56, 48, and 11, 296. And it turns out if you add those together, you get 2121. So it's a way of doing multiplication that's unique, as opposed to the way you were probably all taught. To do division, you do the same thing, but in reverse. So you're still working with doubles, but you end up working backwards in the opposite direction. As I mentioned earlier, the Egyptians do have fractions. To indicate a fraction, they use the mouth sign, so the hieroglyph that looks like a mouth, like that. And that over a number is a particular fraction. The Egyptians almost always worked with numerators of 1. There are only 2 exceptions. They recognized 2/3, so 2 out of 3, and then 3 out of 4. Most everything else was in what we call a unit fraction, 1 over whatever the number is in the bottom. An interesting use of fraction shows up in the measure for grain and beer, the hecot. A hecot is roughly about a gallon. And it gets represented in the parts of the eye of Horus, which are all fractions of the hecot. So here are some fractions. You can see the mouth sign over the actual number. And here's the so-called Hecate in the eye of Horus, where the parts of Horus's eye represent different fractions of a Hecate. So this is 1/32 of a Hecate, 1/16, 1/8, 1/4, 1/2, 1/64. Eye of Horus also has magical associations, protective associations. So you'll see it in lots of different contexts besides mathematical ones. So we could talk a little bit more about Egyptian mathematics, but it gets pretty complicated, and I'm not a mathematician, but the Egyptians certainly knew how to do a lot more, calculating the volumes of geometric figures, for example, doing some equations, so multivariable equations, systems of equations they could do in kind of rudimentary ways. Some of their problems that they work out in their mathematical papyri are worked out with approximate answers, particularly the geometric ones. But the Egyptians did get to pretty good solutions for a lot of the problems that they posed. Keep in mind, though, at the end of the day, all of this had the function of trying to build a pyramid, to keep track of all the goods for the king, to make sure that the state was functioning and that people had what they needed. So the Egyptians really didn't think mathematically in theoretical terms of proofs, for example, for some esoteric physics phenomenon or some mathematical problem that you might solve in calculus today. Instead, it was very practically oriented, and it served its very useful purpose for the Egyptians.